of the Qosmos division, the Networking Information division of ENEA. And our main business today is to review with you our deep inspection technology and how to apply it to NFVI monitoring with DPI probes. We have about, I think I will use about 40 minutes, 30 to 40 minutes, and keep time for questions. Maybe we can take the questions at the end. I will cover first briefly who is ENE Qosmos. Then I will review the Qosmos IX Engine DPI library capabilities and the technology. It's important for everybody to understand what it is. What are the main use cases, where they are used, and how we can leverage the functionality provided by Qosmos IX Engine. As an example, we'll develop how to apply that to NFVI monitoring. We all know that NFV virtualization of the service provider infrastructure is starting nowadays, where projects are getting there, and how to manage NFVI infrastructure relying on DPI is, we think, a fruitful topic. Finally, we'll review some integration model. It will be a bit more technical on how to hook a DPI probe or an application embedding DPI into various virtual switch environments. So let's start and check basically some facts about Qosmos. So Qosmos is a network intelligence division of ENEA. We are the leading vendor of DPI libraries that are embedded into various use cases. We have 75% of market share. We started this business more than 10 years ago, and I've been lucky to reach a significant growth in different markets. We are, and I will review that. We are part of ENEA now since early this year. We've been acquired by ENEA, where we have been identified as a nice complement to the various NFV products that ENEA is pushing to the market, including OPNFV platforms for edge and core platforms, as well as network monitoring tools, network management tools, relying on NetConf. So ENEA has been around for 40 years, starting with a lot of OS and nowadays real-time operating system that are located in radio stations, for example, provided by leading platforms. Many of our phone calls are going through ENEA software. From then on, ENEA has moved into Linux and now in OPNFV and management, and now with the Qosmos in deep packet inspection. So altogether, we are around 500 employees deployed with R&D in Sweden, US, Romania, France, service organization to help our customers deploy our product and tailor them to their need. And but now we'll focus more on Qosmos. Qosmos DPI is a deep packet inspection library and has been very popular on the various security vendors and telecom vendors. For telecom vendors, the main use cases are traffic shaping, service assurance, and big data analytics. So in telecom vendor, for example, we have equipment manufacturer using our deep packet inspection library, IX Engine, inside P gateways, for example. On the security side, we have large networking companies deploying our DPI library into firewalls in order to have next-gen firewalls and for various use cases. So we've been there for quite a long time, and now we are trying to accompany, I'm not sure if it's English, to the market, to SDN and NFV, for example, by having DPI part of SD1 or CPE platforms or virtual CPE core platforms. So Cosmos Intelligence, network intelligence is applied to optimize, monetize, and protect our traffic. These are the very important domain applications. Optimization, it's policy control, SD1, monitoring the quality of service or enforcing quality of service. On the monetization, subscriber analytics and charging applications with virtual CPE can be very important. And all of that, protection is obviously helping next-gen firewall to apply rules not only based on port numbers, but also based on the knowledge of what applications are carrying what traffic, and also providing access to the content of the packets. So we do that by providing visibility to thousands of applications as the traffic is flowing through the embedded application that we support. We identify various applications, we call that classification, and we are able, in particular when the traffic is unclear or when we are behind an SSL proxy, for example, in the enterprise space, to extract a huge number of metadata so that our customers can deploy applications that closely fit their use cases. So some example of vendors using our deep packet inspection, you will find, for example, a lot X4, ETSI, Protei, Empirics, for example, is doing a lot of big data analytics. OpenWave Mobility is providing optimization tools. Polystar and Anrinsu, for example, is doing analytics as well. HP has been using our DPI library for Wi-Fi access, but also for big data analysis. We are working closely with channel partners as well in order to support a lot of different hardware. So we're working with Intel and ARM and Cavium, and also other partners more on the business side, such as HP, in fact, and Capsch or Luxoft, in order to help us deploy applications in various markets. We typically not sell the application ourselves, we sell the X-Engine library, and that allows to support a lot of use cases. Now, the technical space in the telecom is changing rapidly with some new technology that everybody is aware of, such as the standard, the NFV standard pushed by ETSI, and we've been participating to that, including as well as OpenStack and OPNFV, in order to make sure that these coming standard or de facto standards are compatible or enable services that can leverage the application visibility that we can bring to the market. So we've been working with IETF on service chaining, with OpenDaylight on enriching their data model to support layer 7 attributes in the classifiers that are defined in ODL in order to decide what traffic can enter into a chain. We are working with OPNFV as well, and OpenStack, for example, on tap as a service. And with ETSI, we've been working since the start on NFV, defining the NFV architecture, the VNFC, which is one way to consume possibly DPI, not as an API library, but as a virtual machine. And we are continuing this effort to accompany the industry in the standardization body, because we feel it's a long-term investment for the community that is worth pushing. Aside of, just a note to say that aside of Cosmos effort in OPNFV, ENEA has been very active in OPNFV as well as one of the, in particular on porting OPNFV on ARM platforms and providing a Pharos lab, so it's a test lab for OPNFV that allow VNF vendors to test their devices, including VNF vendors supporting DPI on platforms hosted by EMEA in Sweden. So, but now let's focus a little bit on the technical aspects of Qosmos IX Engine. So this is a nice diagram. It looks like a real engine. So and that's the whole objective to describe how fine granular job we have to do at looking at the packet and extracting as they flow through our library the information that they contain. So first, we provide our library, our X Engine library is a set of C libraries, mostly a library for classification and metadata extraction. It is also capable of working with its internal flow manager entity or with an external flow manager entity. The flow manager is here in the picture, and this is the X Engine that can work with an external or internal flow manager. And our job is to take packets coming in and associate them then in flows, and flows being not only identified by their layer 2, layer 4, 5 tuples, but also with more granular information that allow us to not only say what is the protocol stack that is used to transport the packet, the payload, but also what is the nature of the application, and possibly inside an application, how is it used? I mean, is it video or chat, for example, inside Facebook? So our X Engine library is designed to be embedded into applications, so it's able to run on a lot of different hardware. It works on ARM, it works on Intel, and we benchmark it, and we try to optimize it to get the maximum out of the platform we work on. It performs application classification based on stateful analysis and also on statistical analysis for certain protocols. As we analyze the packet, we basically construct a table with information that we extract, and we make this we correlate possibly information collected in different packets into metadata that, for example, a URI or the content of a message, for example, the destination of a message. We correlate information also across flows when needed, in order to be able to identify that a SIP session is on one flow, particular flow is correlated with a video session on the other side. At the same time, as we are doing that, we are doing an ongoing job, because we are supporting a large number of applications, of maintaining, in fact, the protocol, the stack of protocol that we support. We support a large number of protocols, and we have a team responsible for checking that our protocol signatures are kept up to date, and our library can be embedded in such a way that the protocol signature set can be uploaded at runtime without stopping the application. Okay, so we have a question on what happens when we have a HTTPS. Obviously, a lot of the traffic, for example, in the telco market is now encrypted. It doesn't mean that we cannot do many things with encrypted traffic. We can first classify the traffic. Even though the traffic is encrypted, we can identify if it's Google, if it's Facebook, and inside Facebook, what type of service can be applied. And I will basically cover that in the coming slides. But first, we have, just to summarize, we have more than 2,500 protocols classified, a large number of application metadata, and continuously updated signatures. So the benefit basically is for our customers to avoid to have this heavy-duty maintenance work to be done, and also we have the coverage of the traffic worldwide, so that we are aware of new applications when they happen, for example, in Asia. Our customers are letting us know that something happens. We also monitoring specific protocols more closely, because we know they are changing and they are difficult to maintain. For example, like Skype, which is an encrypted protocol. So we provide a lot of work on maintaining a protocol stack and making our engine always more performant in order to support the growth of the number of protocols and metadata that we can extract. That's why most of our customers are happy to give us the job of managing this work of analyzing packet, because it's not enough to build a DPI library once. It's very important to have a set of protocols be updated in proper time and with proper service level agreements that we can provide to our customers. So that's basically using our library provide a short time to market for solution developers, and it offload them from a complex development and allow them to concentrate on the heart of their functionality, be it firewall, NFV1, and so on. That's how we've been able to convince a lot of companies providing PCEF, providing quality of experience, wireless LAN optimization, next-gen firewall, to all leverage our platform. Now, there are different ways to integrate our technologies, our library, depending if you are online, offline, and we will cover some of that. And the use case also are very different if you are a service provider or if you are more looking at the enterprise market space. Our job to cover these two use cases is basically to provide to be efficient at protocol and application updates, as I said. So we have a life cycle where we reverse engineering traces based on captures of traffic that we collect either ourselves or through our partners. And then we develop and decode a set of signatures. Signatures are used to identify uniquely, without false positive, a specific protocol. Then we have a large test and regression infrastructure that is applied. So we make sure that when we bring change to some signatures, it has no effect on the rest of the platform, nor on performance. Then once we have test, we deploy the signatures or the library updates to our customers so that our customers can benefit from the new signatures. When they run the DPI library, they basically see application being classified, they extract metadata. There are still usually a little bit of unknown traffic which is left. And this unknown traffic is a source of information for us in order to detect new changes, new applications that appears, and where we need to focus our attention in order to support emerging applications that are growing at that point in time. So we are covering some protocols with like IP, TCP, standard protocols very closely. These protocols are not evolving too much, and we are focusing on metadata extraction. Then we're focusing on a large number of web applications, file sharing, meeting place. Web applications are the bulk of the signature that we provide. There are thousands of them. We are handling next generation IP-based services like webmails. These are very complex applications that needs to be closely monitored. Peer-to-peer like applications require a lot of attention as well, in particular BitTorrent, because these protocols are changing and they need to be monitored closely. So we have a special focus on those. Desktop sharing is also a very important application for the enterprise space. So we are doing all that, and at the same time we can allow our customers to create their own signatures because they have their specific internal needs. For example, they have application service provider may have an internal application, and we can decide to build signatures and add them to the set of signatures that we are maintaining. Okay, so we are using different techniques for deep packet inspection. We are doing regular expression matching. We decode some protocol using C libraries, TCP, IP, for example. We don't use pattern matching because the format is very stable, so we apply C functions to that. Then regular expression for web. For complex protocol, or encrypted protocol, we use statistical methods or behavioral methods to identify or to classify encrypted traffic. On encrypted traffic, we can use the TLS hello exchange to extract information from like the command name or the DNS information associated with the command name, or the certificate to identify encrypted traffic. Obviously, an encrypted traffic can be classified, and many applications are encrypted. But once we've classified the information, we are not able to look inside this traffic if we see it from our library. Some people are deploying our library behind an SSL proxy. In this case, they are taking the responsibility of decoding the traffic. And that's a general use case in the enterprise that allows to decode some traffic before the SSL proxy in clear, and therefore to extract metadata even though the traffic is encrypted after the SSL proxy. So we are using regex mostly on TCP UDP, advanced traffic analysis, and binary encoded for the bulk of our traffic, and then statistical recognition and behavioral recognition for complex protocols. We have various techniques for that. All in all, we are using 9 classification techniques. Pattern matching is the most used of one. SSL, TSL parsing, quick pattern matching, layer 3, layer 4 information caching, DNS cache, behavioral analytic, heuristic analysis, speed. Sorry. Speed is a statistical way to analyze patterns in exchange of messages. And then we use IP port analysis. So out of these 9 classification, the blue one, all the blue ones you see can be used for decoding encrypted traffic. So we are doing quite a lot in that domain, and this is not diminishing obviously over time. So just to give you a feel for handshake pattern matching, you can look at these slides later on. But we basically, with SSL, we are able to see the common name and the session ID, doing session ID correlation. We can monitor the TLS, the DTLS handshake to classify SRTP flows, and we work with this way with SSL TLS, HTTPS, and many other. The reliability of this method is high, and we do quite a lot of usage of that in order to support encrypted traffic. Statistical heuristic classification is used when non-clear text encryption layer is available. For example, Skype does not rely on SSL TLS, so there is no exchange of certificate that we can look at. At that point, we can look at the exchange of messages, the size, the frequency of message, the burst of messages followed by some different exchange of messages with different size, some patterns inside the size. we can correlate basically these events and by learning from traces, and then have a statistical basically classification of some protocols like BitTorrent, fully encrypted, or Skype. The reliability is medium, but when we compare, for example, our results with Skype compared to other DPI technology, in particular open source DPI technology, we can see that we are much more reliable in the protocol handling of complex encrypted traffic. Okay, so this was a little bit detailed information on the DPI engine, its role, and how we perform that. Let's look at NFVI monitoring use case in order to illustrate and what we do. Here we act basically as a DPI customer providing an application for a certain application domain. So in our haste to prove NFV, we almost forgot monitoring. This is a bit of a joke, but basically it explains that moving from traditional hardware-based silos of application environment, where monitoring was performed by putting hardware probes connected to the wires, connected to tap ports on switches and routers. We are moving now to a world where the applications are virtualized, so they are acting as virtual machines on a VMware or an OpenStack platform, and we suddenly lose track of the networking traffic inside this infrastructure because there is no more place to plug a hardware probe simply in such an environment. And how this is very important in particular because a lot of service providers are now upgrading their network over time, and now it becomes more and more difficult to get new P gateways, new IMS solution, new virtual CP products, which is not virtualized. There was such a request for virtualization solution that all the products built by equipment manufacturers are now virtualized, and therefore, when they are deployed and proven in POC, they are moved to commercial test, and in commercial test, operational people come on board, and now they are not in the same spot they used to be because they suddenly cannot see the traffic between different resources, and they need to rely on new ways to support the applications. This is not going to stop because virtualization applications will be built with virtualization in mind. And when we had previously 1 or 2 VMs providing a function, there will be maybe 10 or more VMs plus a number of containers providing the same solution, benefiting from the technology of virtualization in order to get a better resource usage or better performance, but making the job even more complex of monitoring all that. Just to give you a feel for that, there is a project called Cord. It's basically a central office re-architected as a data center. And there are a number of projects inside Cord that is focused on 5G deployment architecture. So projects work for broadband access, for mobile access, different environment for the infrastructure, radio access networks. And one of the projects is the analytic part of Cord. And the Cord people have identified that virtualization will be used for 5G massively, and there was a need to define the monitoring infrastructure basically from day one with a set of principles in mind. So what they came up with is a set of generic requirements where basically they first separate the data collection, the info collection information coming from different devices into common database and have multiple applications for business analytic and monitoring reason, leveraging this information. So try to separate the various functions, separate the data collection from the use of this data. And the requirements they have on that basic architectural principle is that first, the infrastructure must be scalable and support multi-tenancy. Multi-tenancy in OpenStack, for example, means that you have multiple projects deployed at the same time on a common virtualized infrastructure, and each one has its own virtual network and a set of VMs that it deploys, and his view of his resource is limited to what he is controlling, and is not allowed to communicate to the project and the resource and virtual networks of the tenant or the other tenants on the same network. So the expectation is that VNF vendors will be deployed as tenant, basically. It must be possible to instrument the service in addition to compute and network devices. What this means is that as an FBI administrator is hosting a set of VNF and multiple tenants, the NFVI will be responsible of correlating the information that comes from customer care, where people say this service is not working well, with the view that the VNF vendors have of how this service is behaving from their point of view. So if you buy a VNF from a large equipment manufacturer, it will come with a VNF manager. This VNF manager will monitor the set of resources from the point of view of the tenant, which means that he sees only a subset of the resource of the NFVI infrastructure, so it doesn't know if the host is running on is saturated or is missing disk space or CPUs, for example. He has a limited view, so his view of the world might not be a proper idea of what is really happening in life. So that's very important, therefore, at the NFVI monitoring infrastructure to be able to identify what is the customer view of the traffic. So that's called the service view in here. And therefore, we need to be able to see the service view, we need to apply DPI, because DPI will allow you to see the HTTP response time, the database response time, measure the voice over IP quality of service. And inside an NFVI infrastructure, there will be a lot of NFV, so therefore a lot of traffic. It might not be possible to apply DPI to the whole traffic at the same time. Therefore, there is a requirement identified by core to be able to adjust the level of probing, of data collecting, of probing, of DPI analysis, based on the monitoring function that needs to be applied at a certain point in time. So basically, the probing level, the granularity must be configurable dynamically. That means that the probe needs to be quite smart as a result, and that's a big requirement on the monitoring probe. Obviously, in order to diminish the work done at the business analytics level, it's important to do some pre-aggregation of the data collected by DPI. So with DPI, you can collect response time, but you need to correlate this information with information explaining on which compute host it was collected, it was related to which VNF, to which tenant, in order to help the business analytics application to do a good job of identify if a problem on a particular resource might affect this service or that service. Finally, there is a need to be able to redirect dynamically the traffic collected at one point in the network to a probe VM for specific analysis. So it's a bit like a good old TCP dump. You plug your TCP dump on by doing some wiretapping. Here you need to be able to do that programmatically, and there are ways to do that. For example, in OpenStack with Tap as a Service, which gives a good example of how this could be done in the future, and how we are working on that as well. Okay, so quickly, what we are doing, we are putting a NFV probe inside the NFVI infrastructure, inside the hypervisor, in order to collect the traffic at low granularity using NetFlow and IPFix, in order to feed a traffic matrix, which is made available to OSS and BSS application, business analytic application, in order to have an overall view of the health of NFVI infrastructure. So an OpenStack deployment, sharing a number of NFV and service chains. And then the NFV probe can be reconfigured dynamically using netconf to collect more specifically part of the traffic at high granularity. This is the type of function that we see required by the NFV administrator, so that it can now provide a continuous visibility of existing applications down to the hardware element that are supporting the compute node, the disk that are supporting the function, by having this NFVI probe working inside the infrastructure. So very close to the virtual switch that direct the traffic to the various virtual networks supporting the VNF deployed on this compute node. That allows to accelerate the root cause analysis, because we collect everything at low granularity, and when we have an issue, we can control the level of aggregation and collect at high granularity information in the virtual switch in order to analyze things more deeply. So what is low and high granularity? So low granularity is basically limiting the information you collect in order to not spend CPU cycle on DPI. So you can limit it to layer 2, layer 4 attributes and correlate that with VM information, but not looking into response time, HTTP response time, or database query. High granularity is basically to say, I want the virtual switch to send me information about this VM, and I want to look more in detail to the traffic that comes from this VM. So you will apply DPI to a subset of the traffic, but you will spend more CPU cycles to get more information about the traffic and the services that are used by or delivered by this virtual machine. If we are working at IPFix level, we can collect information which is useful. So we can collect information such as packet loss. We can still see port number, so we can have a feeling for throughput deployed by various VM. But we don't know much about the end user experience of using a service. When you want to troubleshoot an application, you will need to move from, is there a block, a bottleneck at some point in time, which is a layer 2, layer 4 information that we can be derived from analyzing the data, to a question more precise, which is my database performing correctly? And if not, what are the queries that are slow compared to the queries that are fast? And when you are in high granularity mode, you can look at information in detail. Obviously, that generates more information in the traffic matrix, supporting troubleshooting requirement, but it costs you a little bit more, so it's not possible to analyze the whole traffic in a service provider at fine granularity. Okay, so just to technically, what we do basically, we connect to the vSwitch. We capture copies of the traffic that is processed by the OVS or VPP. These are different kind of vSwitches, or OVS DPDK. And the traffic copy, the packet copies are sent to the NFV probe, which is configured by netconf to apply some aggregation and correlation before feeding a traffic matrix via some high-speed messaging protocol such as Kafka. So the NFV probe will do pre-aggregation and correlation. The traffic matrix is the point where dashboards can be built, where business analytics applications can be built exploiting the data delivered by the set of NFV probe deployed in the network. So there is also some syslog capabilities, and the NFV probes need themselves to be managed because they are critical resource. Because the monitoring system itself needs to be monitored and managed, and basically it's a full system that needs to be deployed. So when you deploy a compute node, you need to automatically deploy an NFV probe that register to every switch properly. So we have a question on what are the performance restriction on high granularity case. Is there any public result test? I will show some benchmark on DPI later on to give you a feel of how much traffic DPI can be performed. What we need to keep in mind when you apply performance to DPI is that there is a performance based on classification, which is used, for example, for P gateways, typically because P gateways are interested in what is the type of traffic, but not that much on what's inside the traffic. And in this case, we do not extract metadata, and therefore we have a certain level of performance. When you look in metadata, you tell to the DPI which are the metadata that you want the DPI to extract. So depending on how much metadata you register, the DPI will spend more or less cycles in order to process the traffic. So the performance will vary with the type of your expectation, basically the type of metadata that you think you need in order to solve your problem. Here we are in a monitoring use case, and therefore you use the probe as a first tool to identify or to troubleshoot the system. So you want basically to rely on low granularity to provide you with a stable, consistent, all the time view of the traffic, and you want to use DPI only when you have an issue and only when you look at something specific. So if you troubleshoot, you can expect to degrade a little bit. Possibly there will be no impact, but if you ask for a lot of information for a lot of traffic, this could have some impact. But if you are really in a troubleshooting use case, it means that you have an issue and you need to spend some resource in order to solve this issue. DPI is not too much costly compared to a more intrusive situation where you want to turn on logs at the debug level in your applications in order to try to understand what's going on and then try to reconcile that with information that you get from outside, from the customer care. Because as you turn log, you will slow down your application as well and change basically the problem under analysis. Monitoring, NFVI monitoring as a second user. So the first one we mentioned before was the NFVI administrator. The second user is the NFV administrator. So you have many NFV applications deployed. Each one has an administrator and a VNF manager, and they may need to capture traffic, let alone to correlate their view of the traffic with the view of the traffic and the service and the response time, which is claimed by the NFVI administrator. So the NFV probes can be deployed as well in the virtual networks of the VNF vendors in order to provide the same view, the same type of information, but limited to basically the virtual network of the NFV, in order to support different functions. So basically helping on troubleshooting case, but also monitoring alarms for VNF, drill down basically and troubleshoot specific VNF when troubleshooting service error. So in this case, we try to rely on a function called tap as a service. Tap as a service is a project in OpenStack that allows you to redirect the traffic from one VM to another one. So it's supported by OVS, typically, virtual switches. We are working with a port of tap as a service to VPP. VPP is also a very important virtual switch in particular for service provider more than for cloud, where the performance is less of an issue than for service provider virtualized infrastructures, for NFV vendors. So TAP as a service allows you to route selected traffic to a probe, and then you configure your probe, just as we did before, to decide what you want to look at. Okay, so the Qosmos probe basically is deployed in a virtualized environment as a vProbe. It's a ready-to-use DPI application. What does it do? It performs packet captures and deep packet inspection and process data. In particular, doing correlation and aggregation of information. For example, trying to correlate the traffic with a container information, or try to look at response time and associate response time to a particular user if you have the ability to correlate an IP address to a subscriber. It's a modular. We had to build the virtual probe or the Qosmos probe as a modular architecture because there are many use cases and many deployment scenarios. And in particular, it's important to be able to feed a variety of backend database, like time series database. Example of the time series database are Elasticsearch or InfluxDB. But there are also database APIs used by OpenStack that we can feed. There are projects in OpenStack or NFV called Doctor, for example, that provides an interface where we can integrate as well. And with the virtual probe, we show how to customize dashboards that are used on top of these database in order to have an open source visualization based summary of different view of the network. For example, we can look at protocols per applications. We can look at protocols that are misused for security reasons. We can look at response time. We can look at encrypted traffic and how it flows in the network. We can look at how what VMs rely on for each VM, on which other VMs they rely on in order to identify dependencies between VMs. So there are a lot of information we can extract from the data that is aggregated into these time series open source database that are fed by the virtual probes. So give you a view of a virtual probe. It's made of a series of layers, each one supporting a number of modules. So input modules and output modules are traditional, basically, way to collect information and send information. So we have DPDK collection and PCAP collection. We have NFQ in order to coexist, allow the probe to run in a smaller device like universal CPEs. NetMap is used, for example, to integrate with high performance the probe with VPP. So we have a number of input modules, and then we send the traffic to the DPI library and other libraries that are jointly analyzing the traffic. So DPI is a layer 7 module in the middle here. We have deep file inspection, which is used in the enterprise network space to go deeper even deeper in the analysis of the payload transported by file transfer or email in order to do applications such as data leak prevention. We have a GTP library module that allows to analyze the traffic when you collect it before the P gateway in a mobile network, and in order to correlate basically the traffic flow with subscriber information. Then we have a number of modules that provide lookups, so we can do reverse DNS, we can identify the containers associated with the resource that we are monitoring, or the VMs. These are examples. Then we basically perform, it's not shown in this diagram, aggregation of information, so we can try to aggregate counters such as traffic per subscriber and per application in order to feed the database with not only detailed information but pre-aggregated information, which helps provide reports, ongoing reports for data usage and trending, to support trending. Then we have output modules to format and send information to different backend systems. In addition to that, we have modules such as contract, which are used to feed back information to the virtual switch. So we can, as we analyze and classify traffic, we basically have very useful information. Flow. A flow is an FTP application, a video application. So we can pass information via the contract module to a contract table, a Linux contract table. And this contract table can be accessed by the virtual switch, or it can be, we can do the same with VPP. We're using another technique, using a flow table. And this can be used, for example, for the virtual switch in order to apply traffic shaping or to apply firewalling rules, leveraging the classification result that we pass with this module. So it's an output module, but it's not an output module to the database. It's an output module contract back to the virtual switch that provides basically, that makes the probe not completely passive. In fact, it provides a loopback mechanism from the probe to the network. And it has some use cases. One of the use cases we have like for that is what we call offloading. And that basically is the case where we want to limit the number of packets which are sent to the probe. So once a flow is classified, we can tell to the virtual switch, stop sending more packets for that flow to the virtual probe because we are done with classification. So that's very useful. So basically, to finish on this section, we have basically a probe that is able to collect metadata and metrics. Then we apply correlation, aggregation, and filtering in another ETL layer that will basically provide information in a database. And this database can be used to perform dashboards. This is a view of the dashboard that we provide. And anybody can build this dashboard. It's a configuration using Kibana for this particular example, where we monitor the traffic globally for this switch, and we break it down, and we can break it down in many different ways, resulting from the richness of information that we have in this traffic matrix. And the dashboards basically can be built in order to solve a particular troubleshooting scenario. So basically, as a result, with the vProbe deployed in an NVI infrastructure, we can restore visibility, and that's we think it's going to be a very important key success factor for deployment of NFV services. So I'll just go over a couple of models just to give you a view of how to integrate a probe. So what basically our customers are doing to integrate their software with virtual switches. It's the same model. So when we integrate with OVS, we basically, as I described, leverage the contract table in Linux kernel in order to mark the flows with the result of classification that allows to perform in OVS some QoS and dropping and out and steering of traffic based on a classification result. So we send copy of the traffic to the NFV probe, and the NFV probe feeds the contract table as a result. And offloading allows us to, as I said, to stop sending traffic to the NFV probe once a flow has been classified. And it's very important because in DPI, we need, on the average, 2 or 3 packets in a flow in order to classify it. We're not talking about metadata extraction, but really only to classify it, which means that for long flow, we can save quite a lot of CPUs cycles to avoid to examine a lot of packets belonging to that flow pass the classification result. So when we do offloading, we need to process only 10% of the total set of packets that are sent to the OVS switch. So this is an example of an OVS configuration. When we want to do offloading, you need to configure rules in OVS to support offloading. You can study that, but basically it shows that we rely on NFQ in this case, and we recirculate the traffic copied by the OVS to the vProbe, and we recirculate the packet so that it's then tested against classification result in order to provide decisions. This means that if we want to support offloading, we need to have OVS to know about monitoring. This is a limitation in OVS. We don't have the same limitation in VPP. For performance reasons, we do regularly some benchmarks. So here are some benchmarks of the DPI library classification performance. We look at the number of threads. So these are hyperthreads. So we have two threads per core, and in this case, we show the performance based on the number of cores that we see on Haswell and Broadwell Intel processors. So on the average, we see a very good scalability. So it stops in Haswell because we have no more processors on the device. And we see on the average very good linearity and a classification cost of allowing us to process 6.5 gigabits per second for classification on a traffic which is a service provider, North American telco pattern. So it's 400 bytes packets and a good mix of protocols as expected into a service provider network. So the performance is good. This doesn't count the data collection. It's only the DPI library performance impact. So that gives you a feel for the DPI, the cost of DPI. Typically people deploy right now 10 gig networks, so 10 gig networks with reasonably can be deployed with a few cores, 4 or 5 cores if we count data acquisition, for example. Vector packet processing, I won't go in detail, but it's a Linux FD.io virtual switch. It's an open source project which has a great potential in terms of performance to support virtual switch, but also it can be used to build VNFs, and that's very important because it contains all the functions to capture, analyze traffic, to perform routing and switching. It's all packaged, and it's also it supports a nice plugin architecture that allows anybody to add information. So what we did in VPP, we added support for flow tables because we need flow tables to perform offloading, and we connected it to the NFV probe. So we use NetMap to send traffic to the NFV probe, and we use the VPP binary control API to send back information to VPP once we perform classification. So this allows us to support millions of packets per second exchange between VPP and NFV probe. So that's a good example of a high performance NFV probe integration. And what is different from OVS in this case is that if you configure VPP for routing, firewalling functions or traffic shaping, you will add your own plugin, and the monitoring function will be orthogonal to all these software. So there will be no conflicts of rules as there may be in OVS if you want to control the configuration of OVS for monitoring purposes. In VPP, you add your own plugin, and each plugin acts independently, which is a very good quality, in addition to the sheer performance of VPP. We are pushing VPP a little bit in OPNFV, and there are OPNFV an OPNFV port of OpenStack and OpenDaylight on top of VPP. There are a number of VPP projects in OpenStack, including support for service chaining. And therefore, we felt it was important to be able to have tap as a service function with VPP as well. So we have been contributing to OpenStack project and to VPP, the software for tap as a service, in order to enable this very important functionality for monitoring purposes. Okay, so that's basically what I wanted to share with you. We have still some time for a few questions. So if anybody has questions, I'm available. So I have questions on the performance results were on VPP or OVS. The performance information that I shared with you was only the library itself. So the software to do this test is basically to put the trace in memory and to pass the packet directly to the library. So it doesn't count the data collection of VPP and OVS. We can share offline if you're interested information about performance with OVS and VPP. It really depends if you're using OVS or VS DPDK, if the probe is collected using port mirroring, or if it's used using tap as a service. I mean, they are complex. But basically, if you are doing port mirroring for VPP, you can basically serve 10 gigabits per second of traffic to the probe, or 18 gigabits of traffic to the probe through NetMap. Do you have any open source project? What we do is we sell the X engine is an SDK. It's not open source because we spend quite a lot of resources on updating the signatures. But what we do is we try to work with our customers in such a way that it's a win-win situation, meaning that we are not trying to cost more than what makes sense based on the information that we provide for the use case supported. So we've been working with a large number of suppliers in different use cases, so we know how to value properly and at the right level the license cost of our X engine library. And obviously, we are very open to discuss that with anybody who would be interested in knowing more. All right. Well, thank you, everybody. I don't see any more questions, so I was very happy to be able to deliver this little. One more question, maybe. What do you think about OpenFlow? Do you have any deployment integration with OpenFlow controller? We've done some integration in POCs with for service chaining with OpenDaylight. OpenFlow is fine for cloud-based services. It's still a question for me for NFV if you need to dynamically change the configuration of the OVS at runtime. For example, try to give you an analogy. P gateways, for example, they have an interface to PCRF, so policy resource controller functions. And there is the possibility of having the PCRF send rules dynamically to put some pattern that needs to be charged differently. But nobody is using that. Everybody is trying to fix rules, to work with default rules, configure once for all, and delivering the service when you're delivering the P gateway service and you analyze the flow in real time, you don't take new role at real time. And that's the same for OpenFlow. OpenFlow can work fine with a set of rules preloaded and can support with obvious DPDK quite a lot of traffic. In particular, considering the performance bottleneck that exists right now in how virtual machine can talk to virtual switch at 4 million packets per second. So OVS can work with fixed set of rules, not too many, maybe thousands of rules, but not 10,000. But rules that don't change. If you're trying to create rules dynamically, OpenFlow is not good for that use case. In cloud, when you have a small amount of traffic, changing the rule because you have a new customer is not an issue. But the traffic in the cloud is really much smaller than the traffic expected by telco in their virtualized infrastructure. All right. Thank you, everybody. Spasiba. That's the whole Russian I can say. It was a pleasure for me, and I hope it was useful. Thank you.